Maxfield visiting us from UChicago, and he'll be here through Wednesday if you want to come and discuss with him. He's in 422, I think is the office number. Also tonight, some of us are going out to dinner at some time, at some place. If you're interested, let me know. Now we can hear what Travis will tell us about the conformal anomaly of M5 grains.
Okay. So I'd like to start just by thanking you for having me here. I'm really excited to be here. I'm astounded by the beauty of this building. It's fantastic. So today I'm going to tell you about some work that I did about a year and a half ago with my advisor, Safi. There was a recent nod to this work at Strings 13, if you were paying attention. I'm not Maxwell, but this is the right reference. And I hope this work isn't complicated, as Mike Douglas said, but you know, of course I'm biased. So if you do think it's complicated, I want to use this as an invitation to try to ask me questions, interrupt me. Don't go away thinking that it's complicated. So, like Mike Douglas said, what we give is a field theory demonstration, the first one I know of the cubic growth of the conformal anomaly of two zero theories. And the way we do that is by using maximal supersymmetry to relate higher derivative interactions on the Coulomb range between 4 and 6 dimensions. It turns out that the conformal anomaly is captured by a certain higher derivative correction on the Coulomb range. And in the end, what we get is a relation between the conformal anomalies of the 4-dimensional maximal Super-Yang-Mills theory and the 6-dimensional 2-0 theory. Now, if none of that made any sense, if you don't know what a 2-0 theory is, that's okay, because we're going to start by reviewing the relevant details of M5 brains and the 2-0 theories that come about from them. Then, since effective actions are going to be a key player in this talk, and especially ones that enjoy supersymmetry, I'm going to tell you a little bit about how those two things play together. I'm going to tell you about how the conformal anomaly arises from, is manifest on the Coulomb branch. Then I'm going to give you some flavor about actually the work that we did, which is seeing how Coulomb branch interactions get constrained by supersymmetry, maximal supersymmetry. Finally, I'll get to the cubic and a bit of discussion, and I'll be peppering discussion, of course, along the way. Okay, so 2-0 theories are 6-dimensional interacting superconformal theories. They possess a chiral n equals 2 supersymmetry. This n that I've been using as a subscript here refers to the rank of an ADE Lie algebra, which is associated with the theories. In the A case, it's easiest, I think, to visualize these theories as being the low energy limit of n+1 coincident M5 brains. This is completely analogous to the situation with DP brains, where if you stack n+1 of them on top of each other in the low energy, there's an SUN p+1 dimensional maximal Yang-Mills gauge theory. These 6-dimensional theories are fundamental in a certain sense. One obvious thing is that Nam told us that 6 dimensions is the highest dimension that we can get interacting superconformal field theories. And so from torus compactification, we can relate this theory to all of the other lower dimensional maximal Yang-Mills theories. A particularly interesting example that will be paramount in this talk is compactification on a 2 torus, which gives the 4-dimensional n equals 4 super Yang-Mills theory. The coupling of that theory then descends from the complex structure of the 2 torus. And this gives a geometric realization of the S-duality of the n equals 4 theory. So that's pretty interesting. But in addition to doing just simple torus compactifications, it's been very fruitful lately for people to do more complicated compactifications, twisted compactifications on punctured Riemann surfaces and 3 manifolds, and this has resulted in a lot of interesting duality conjectures between different theories in different dimensions. And this is just scratching the surface of the interest in these 2-0 theories. They're used in
sorry, in 3D case, what kind of 3 manifolds are considered?
I'm not sure what kind of 3 manifolds are considered.
They're not merely Riemann surfaces times a circular, are they?
I don't think so.
Okay.
I think they do more general 3 manifolds.
The typical thing is hyperbolic with boundary.
Mm-hmm.
Well, now these 2-0 theories are probably as mysterious as they are interesting. One obvious way they're mysterious is that there's no known Lagrangian for them. So I wasn't just being coy when I didn't write down a Lagrangian at first. There isn't a known Lagrangian. And this may be expected to be the case, seeing as being descended from M theory, there's no dimensionless coupling in the theory. So you can interpret this as saying any coupling constant is inherently more than one, and the theories are inherently quantum mechanical. There's no classical limit in which you can dial some interaction parameter down to zero and look at a Lagrangian. Another interesting and mysterious property of these theories, which will be central to this talk, is the cubic growth of the conformal anomaly and associated quantities. So this has been seen in a number of ways, mostly through ADS-CFT and supergravity. And what's mysterious here is, especially when it's being compared to the n=4 theory in 4 dimensions, where the conformal anomaly and the other quantities grow like n squared. And this can be interpreted as roughly just counting the size of these n by n matrices that make up the degrees of freedom in for example, the SUN or another n=48 in this theory. Okay, so in the past, a number of ways that people have attacked this theory is, like I said, from supergravity and ADS-CFT. There's a number of other ways being pursued right now, including looking at theories with rather than 2,0 but 1,0 supersymmetry. But another way to get a handle on these theories is by actually flowing to the Coulomb branch. And so the picture here is, again, very analogous to what happens with D3 branes and n=4 supergang mills. So the theories possess a moduli space describing the positions of the relative positions of the 5 branes in the transverse R5. And so if we have a number of them stacked on top of each other, we can imagine just pulling them apart. And what this does is introduces a scale by giving a vacuum expectation value of some scalar operator, and induces generically a flow in the infrared to a U1 to the n gauge theory, where each U1 factor here is corresponding to the degrees of freedom living on a single M5 brane. This theory now, though, has a high energy cutoff given by the vacuum expectation value, and so in principle there will be corrections, interactions that we've sort of morally integrated out from between these different M5 branes, which in the M theory picture look like M2 branes stretched between the M5 branes, which become massive states, morally speaking.
In this case, on each one of these M5 branes, we do know a Lagrangian field theory, correct?
Yes. So now that we've started talking about just individual M5 branes, we actually can discuss more details about the actual theory living on a single M5 brane. Each M5 brane supports a 2-0 tensor multiplet, and the field content is given here. There's a 2-form gauge potential, a higher form analog of the 1-form A field in Maxwell theories. It possesses gauge invariance in which it shifts by d over 1 form. The field strength of this 2-form is self-dual. And then additionally, there are 5 scalars which transform into the vector of the spin 5R symmetry. These scalars can be seen as just describing the position of the branes in the transverse R5 space. Right, so these are M5 branes at a 6-dimensional low volume with an 11-dimensional supergravity, and so there's a 5-dimensional transverse space, and each of these scalars describe a position in that space. And because it's a supersymmetric theory, we have to round out the degrees of freedom with some fermions. In this case, there are 16 of them. The canonical scaling dimensions of these fields are different from what you're used to in Maxwell theory, which really owes its origin to being a theory of a 2-form, and I've written them here, and there they are. The B field scales as dimension 2, and the fermion field is determined, its scaling dimension is determined by supersymmetry. So now though, I've said how we get to the Coulomb branch. So now we'd like to look at what is the form of the Coulomb branch effective action. And I'm going to use, of course, the 2-0 theory as a way of a specific example for describing general supersymmetric Coulomb branch actions, because a little later we'll jump down to 4 dimensions and we'll use sort of the same principles. But for now it'll be simpler to just consider a rank 1 case. That is, we just have 2 branes, we separate them, and we just look at the single massless multiplet on the Coulomb branch which survives, which describes the relative degrees of freedom between the 2 branes.
So
Now,
in general, you would need something like a theory of non-abelian tensor multiplets?
for
Just provide coordinate functions?
yes, yeah, at the conformal point, and yeah, there would be some, say, non-abelian tensor multiplets, but of course we don't know how to describe that. So we're just looking at the Coulomb branch point where we can just describe the free theory, just n copies of the free theory, which have some higher derivative interactions between them, which we'll get to. Okay, so now if you're familiar with these 2-0 theories, you're probably shaking your head because this 2-derivative action, which I've written down being the leading interaction on the Coulomb branch, actually doesn't exist. In particular, this kinetic term for the B field vanishes by the self-duality of the H field, but this is a subtlety that we're just going to ignore. You can think of it as the way the self-dual 5-form field strength is dealt with in type 2B. Or you can just think of this action as being more of a mnemonic. See, the equations of motion that derive from this action, supplemented by a self-duality condition for the field strength, are well-defined. The action itself is not well-defined, but we can just consider actions because they're convenient, and really the equations of motion are what we're dealing with.
Like this democratic formalism.
Yeah, it has some similarities to that. I mean, there's subtleties with dealing with self-dual D over 2 forms in D dimensions. So like the self-dual 5 form in type 2D. Yeah.
Concerning free versus interacting,
Sorry.
is that given a single M5 brane, isn't it the case that there is an interacting conformal field theory for a single M5 brane? Which can be obtained from the covariant M5 brane equations and then gauge fixing. I mean, M5 branes in ADS7 cross 4 sphere background.
Okay.
Because the background has ADS7 symmetry, there is a conformal symmetry group in 6D. There is an interacting theory. Why is it that you're not considering that theory?
Sorry, you're saying that the theory on a single M5 brane is interacting, being dual to the ADS7 cross S4?
Yes, it's interacting Waldman field theory. It was studied by Kelosh, Townsend, and others.
Oh, you're saying something like a DBI action, the analog of the DBI
Yes,
action.
exactly.
Right.
Exactly.
Yeah, so that's another thing which is separate from this. So that's actually that's a supergravity action with derivative expansions, or derivatives expanded in powers of like 1 over L Planck, for example. That keeps L Planck in the game and expands in orders of L Planck. This is just the field theory, where the only on the Coulomb branch, the only scale is just the vacuum, the separation of the branes, the depth of the. I think it's different from this Coulomb branch action, but I'm not certain how. There probably are relations between them, and in fact, shortly after this paper came out, Elvang and some collaborators also found the n cubed from this analog of the DBI action for the single M5 brane. And so there probably is some sort of way to map between these two things, but this is not, at least obviously, I think, the same as that. Okay, so, right, so this action, which is the leading 2-derivative action, enjoys a supersymmetry, which I've given here. And the subscript, which I note here, the zeros and the twos, so the zero here is in particular just referencing the fact that these are the leading supersymmetry transformations. We'll be wanting to deal with a higher derivative expansion on the equivalent branch, and so we will actually need to modify the supersymmetry transformations, and that will come with its own subscripts. So let's actually do that. At the next order, at 4 derivatives, we can have a whole new action. We have a whole new action which is at 4 derivative order, but from the Susie transformations, we see that there's some subtlety in the sense that fermions and derivatives get exchanged via supersymmetry. So rather than just talking about derivatives, we actually need to expand things in terms of this supersymmetric parameter, little n, which is counting the number of derivatives in an operator plus half the number of fermions. And in principle, then all of the operators with a given value of n will be related by supersymmetry. So as an example, I've written here the n equals 4 action, which, so let me describe it. It starts with just some overall coefficient in front of the action, which, like I said, everything inside of the parentheses will be related by supersymmetry. So this overall coefficient is just keeping track of the overall, say, scaling of this 4 derivative action.
This is still meant to be conformal invariant, correct?
Well, it's spontaneously broken. It has spontaneously broken conformal invariance, but yes, yeah, it is still conformally invariant.
Well, if phi is not constant, why is there a breaking, spontaneous breaking?
Because we've given phi a vacuum expectation, a non-zero vacuum.
Oh, so it's meant to be a constant, this phi?
Well, this phi is meant to be interpreted as expanded around its bev. This is the phi field which still has a non-zero bev. So this action is interpreted as an expansion in away from phi equals say b, where b is the bev.
But if I leave phi as a scalar field,
Yes.
assign a while weight to it so that it transforms under scaling.
Yes.
You can engineer such actions to be at least while invariant, right? And possibly conformally invariant. That's not what you want to do?
I think it is, but once we give phi a vacuum expectation,
Then it will
then
be
we're
broken.
saying we are also transforming the bev, which I think is just the way that conformal symmetry is still manifest once it's spontaneously broken. We transform the fields and also the bev. This is the leftover. This is the transformation that would give some Lord identities still. Okay, so right, this is the overall 4 derivative action. Where, let me describe what's in parentheses. In the numerators, we have all the possible operators composed of the h, phi, and the psi fields with n equals 4, that is up to 4 derivatives and up to 8 fermions and everything in between. And in the numerator, we just have powers of phi, which should be interpreted as the bev of phi. And these are just stuck in with the correct powers in order to get an operator which has mass dimension 6. And the reason we know the powers is because the 2-0 theory, being a conformal theory, has no dimensionful parameters in it. So the only dimension in the game is just phi. And so we just stick in the right powers. Like I said, at this order, supersymmetry needs to be modified. So we add to the previous supersymmetry transformations these transformations where, like I said, I'll add a new subscript referring to these being not the leading order, but the next 2 leading order supersymmetry transformations. And we parameterize these Susie transformations with these undetermined functions, k, n, and n, which are themselves higher order in this parameter n. One thing to note is that we're adding these Susie transformations in order to make the combined 2 and 4 derivative actions supersymmetric. And the way that works is by a mixing between these transformations acting on the previous 2 derivative action and the original transformations acting on this action. And in order for those 2 things to be able to mix together, it's necessary that these Susie transformations also have to scale with this same coefficient. Yeah.
So when you construct this term, will you know that it's the only one that this word that you could have written out, or
This action? Right, that's a good question. So you've beaten me to a statement I was going to make in a number of slides, and it's fine to make it now. It is known, so we're dealing in 6 dimensions where, you know, it's a little hairy to say very exact things, but it is known that for the analogous case where we consider, say, D0 brane quantum mechanics, or even in 4 dimensions in the n equals 4 theory, that there is just one super invariant which describes all of the 4 derivative operators that show up on the Coulomb branch. And I think it's reasonable then to assume that it is the case in 6 dimensions, that there's just one super invariant, especially at this order of 4 derivatives. But it isn't strictly known. We will be assuming it, however.
because otherwise it would somehow have to vanish when you come back to find out.
Yes, yeah, exactly. Right, if there were another super invariant, it would have to go away or somehow mix with the n equals, with the one super invariant in 4 dimensions.
I see.
So I think it's reasonable to believe that this case it is.
And what's the meaning of C46?
So right now it's just a number, right? There's no couplet constant in the 2-0 theory, so it's just a number which keeps track of the overall scale of this 4 derivative action. And by scale, I just mean number, the way that you can think of it very morally as being determined by like a 1-loop calculation. If I had, that doesn't mean much in this case, but had I been talking about 4-dimensional n equals 4 theory, then this would just be some 1-loop coefficient, which you get from doing an exact
But the
calculation.
theory you start with is 3. How can I generate any 1-loop effect?
Well, the theory we started with is a theory of 2 interacting n5 branes which have been separated.
Oh.
And we've integrated out these massive self-dual strings from the n2 branes stretching between them. So if we knew the microscopic degrees of freedom from the 2-0 theory, then you would say, okay, let's just start at the conformal point. We know all the fields. Give a bev to some operator. We give some fields mass. We integrate them out. And this is just some Wilson coefficient from that RG flow, which would be determined from the microscopic degrees of freedom. In the case of n equals 4 Yang-Mills, it could have a G-Yang-Mills squared dependence, right? It could be telling you what order in what loop order this is. In n equals 4, these terms are known to be 1-loop exact, so it has no G-Yang-Mills dependence. So it is in that case still just a number. But for us, it'll just be important when we start tracking n dependence. It will depend on n, the rank of the theory later. That's why it's been stuck here. Okay, any other questions? Yeah.
Is it obvious that it's fine to restrict to linear terms and fermions in the Susie transformation?
The K, the N, and the M will depend
Oh, okay,
on all of the fields.
Okay, got it.
Yeah. And it's tough to find these, but it's enough to just say that they're of this order and they can be they depend on the fields.
Mhm.
Have they been found, those objects?
Not in 6 dimensions. In n equals 8 quantum mechanics, they were found in a particular example a long time ago. But
For your purposes, you won't need their exact form then?
we don't need their form. We only need to know that they're of order, this particular order,
Okay.
n equals 2, 2, and 3. We don't need to know that though.
So the actual order is supposed to be an ansatz, or?
No, it's just a schematic for all of the possible terms which can contribute in this
So there
order.
are no couples between H and psi, for example?
Right, so there will be overall coefficients, of course, between these, which are determined by supersymmetry. Everything in parentheses has to be related by supersymmetry. From Andy's question, we're assuming that. And so there will be coefficients. I mean, this is supposed to be taken very schematically. This will be the star of the show here, the 8 fermion term, and I'll talk more about that in a less schematic way shortly. But in general, this is just describing what sort of operators can contribute to this one in terms of expansion.
Can you use filter redefinition to remove some of the terms?
Probably. I mean, yes, field redefinitions will come in. For our purposes, we won't care about anything which is, I mean, there will be certain terms which will have to be there, like the term with the most number of fermions. I don't think can be redefined away. and that will be the star of our show. The rest of the operators can probably be mixed around by theory definitions. Modulo then the supersymmetry transformations also have to. The whole thing has to be supersymmetric still. Yeah.
What is it going to be also about symmetry?
Well, it's. Right, yes. Define away the question. I mean, I think, when I say unique, I mean that it's a single superinvariant. Like, if there were, say, a superspace, it would be just one single operator that is integrated over superspace. And for a given Susie transformation, a given set of Susie transformations, which themselves will change under field definitions, then there's only one such superinvariant. But I don't see why both the operators and the Susie transformations could really change. But I'm not sure.
By the way, can this arise, this stuff you've written on the board, can it not arise from the Bornefeld type action? Because there will be higher and higher powers of H coming in.
Yeah,
and
things
B5.
which
Could
look
that
like
be the
this
relation
do-
you're alluding to, perhaps?
Yeah, things like this do show up in expansions of the
Right,
the
yeah.
PI action, but, I mean, in that case, there still is this L blank, and I'm not sure exactly the map between these two, but it's
This
interesting.
L1 paper, the paper you mentioned earlier,
Yeah.
does it make connection with this?
No, not directly. No, I don't think there's an obvious map between the Coulomb branch effective action and the DPI action.
Okay.
Okay, so we'll have to go up to 6 derivatives in this case. So this is just an example, again, schematically, of the 6 derivative action. Again, there's a coefficient sitting out in front so previously the 4 here was referring to 4 derivative, and the 6 is in 6 dimensions because we'll be jumping between dimensions. And here now we have a 6 derivative in 6 dimension coupling. Again, schematically, all of these operators are just the 6 derivative and their Susie completion operators. And below we just have phi's to make it a mass dimension 6 operator. So again, I've lied by putting this term on here. It turns out, sort of surprisingly, that there isn't any 12 fermion term. And this just pops out of the group theory, which describes the representations which can come out of a 12 fermion term, taking the wedge product of 12 of these fermions in their particular representations. We'll have to actually concern ourselves with the term with the next highest most fermions, but it won't really affect the flow much. But it is interesting because in comparison to n equals 4 theories in 4 dimensions, there is, in all of the other theories like quantum mechanics, there are 12 fermion terms. But in the 6D theory, there are not.
What does subscript 1 mean here? 2, 0 subscript 1.
I mean, yeah, the rank 1 theory. So I was previously using n to define the rank of the algebra, and so this is the A1 theory, the SE2 theory associated with 2 rings. So that we're only talking about rank 1 for now. Okay, so now I've written out the Coulomb branch effective action. Now you might be asking, what is the relation to the conformal anomaly? How does it show up on the Coulomb branch? And the story here is very analogous to the story for the chiral anomaly and Tuft anomaly matching, which tells us that chiral anomalies are matched between theories which are connected by an RG flow. And in fact, you would expect it in supersymmetric theories because the chiral anomaly is in the same supermultiplet as the conformal anomaly. So somewhat recently, it was shown that a conformal anomaly is conserved on the Coulomb branch. So 2 theories connected on the Coulomb branch, the conformal anomaly of the theory has to match that at the conformal point. But in general, the CFT, and this is independent of dimension, in general, well, this is in strictly, this is in 4 or 6 dimensions, or in 2, let's say. The ultraviolet CFT and the infrared CFT have different conformal anomalies. So we need something like a Wess-Zumino term in effective action in order to make up the difference in the conformal anomalies. So in the case of, in a d-dimensional effective action, then the Wess-Zumino term takes something that looks like this, where we've got the difference in the ultraviolet and the infrared conformal anomalies. And then there's some d, this is supposed to be the dimension of the theory, some d derivatives acting on tau, which is the Namble-Goldstone boson associated to spontaneously broken conformal invariance. Right, so I haven't shown you really any details, but the idea to keep in mind here is just that chiral anomalies and conformal anomalies are in the same supermultiplet, and you know and believe and trust chiral anomaly matching, so it has to be the case as well for the conformal anomaly. And we'll just need that the conformal anomaly looks something like this, which was worked out by Schwimmer and Thiessen, and later Komodatsky and Schwimmer in their proof of the A theorem. And then it was worked out by, well, you can find it in our paper. It was worked out by an earlier in 6 dimensions. But these extra, there are other terms also in the Wess-Zumino action, but this is really the term that will be.
Where is the chiral anomaly coming from? There's no vector field around.
It's, yeah, I mean, so the theory is chiral because of the supersymmetry, but it's the spin 5 are, there are chiral fermions in the theory because of the supersymmetry.
Yes, but when you talk about chiral anomaly, what comes to mind is some Young-Mills field or some gauge field. Typically, that's not what you mean by chiral.
Associated with an R symmetry, right? It's when you
Yeah, but
turn
that's
on
a
the-
rigid symmetry. It looks to me. There's no vector that gauges R symmetry, right?
Well, isn't that always the case with the chiral anomaly, that you have some sort of global
Oh, it's
chiral
an
symmetry?
anomaly in the rigid symmetry. Sorry,
Yes,
sorry.
yes,
Okay.
it's not a gauge anomaly.
Oh, okay, sorry.
Okay. So we'll be using this form of the Wess-Zumino terms in the effective action. That will be important for us. Now those terms actually are related to terms I've shown you, because in either the 2-0 or the n=4 theory, we can define this Namble-Goldstone boson, the dilaton tau, in terms of some, say, radial component of the scalar fields. Here V is just an overall vacuum expectation value for the fields. And with this definition of the dilaton, then these couplings, which I showed you earlier, showing up in the case of 6 dimensions in the 6th derivative action, are exactly just the Wess-Zumino terms that I just told you about. So we've already seen these Wess-Zumino terms showing up in the Coulomb branch action. Or in other words, in order to learn about conformal anomalies on the Coulomb branch, we should study terms like this. But that's in principle hard, especially because we don't know the microscopic degrees of freedom. So instead, we'll like to study terms that supersymmetry tells us are related to those terms, which supersymmetry constrains strongly. That is, terms which have only fermions and no derivatives. So this would have been the side to the 12th term that I told you doesn't exist. But instead, what I mean here is just the term in the effective action which with the most number of fermions. And I guess I already covered this. I said that it is, for the 4 derivative action, in quantum mechanics and in d=4, it's known that these terms with derivatives acting on the scalar fields are related by supersymmetry to terms without any derivatives. It's likely to be true in 6 dimensions, and we'll assume that's the case. Okay, so now I've said that supersymmetry allows us to study these fermion terms, so what actually can supersymmetry tell us about them? So for this, we'll start with just the 4 derivative action, and we consider the combined, I'll refer to these as the 0 and 2 derivative, respectively, Susie transformations acting on the combined 2 and 4 derivative Susie supersymmetric actions. And this breaks up into 3 pieces. The first of which vanishes because we've already said the 2 derivative action is supersymmetric. The last of these pieces is higher order in this derivative counting, So it's not going to contribute at this order. We've just truncated ourselves to this Susie counting parameter n equals to 4, which is just these two terms, which will actually give interesting constraints. So we'll take a look at those. In the leading Susie transformations of the four derivative action, we'll look at the, quote, top form, which is just the term with the most number of fermions. So schematically, this form is written in this way, which is just a function of the scalar fields multiplied by some 8 fermion term. Right, because it has the most number of fermions, it has 8 fermions in the four derivative action, it can't have any derivatives, so it can't have any H fields. And gauge invariance says it can't have any B fields, so it's only scalar fields and fermions. A little less schematically, we can write this as being some sum of these spin 5 tensors T, which are formed out of 8 fermions. And I've just written them in terms of irrepresentations, irreducible representations, which come out of the wedge product of 8 fermions. And there's just, in this case, 5 of them that can show up, depending on how many symmetric and traceless spin 5R vector indices it has. And in order to make, of course, a spin 5 invariant operator, we need to contract it with a certain number of scalars. So I'll refer to this term as, say, the 4 scalar term, et cetera, the 1 scalar and the 0 scalar terms. Now, when we act with the leading supersymmetry transformations on such a top form, what we get is either a 9 fermion term or a 7 fermion term, depending on whether we act the Susie transformations on the scalar fields or whether we act them on the fermions. We'll focus on the 9 fermion term, which I've written out here, because interestingly, there's no other term in the Susie transformation of this action of this order that gives 9 fermions. And so this is how it earned the name top form, because this Susie transformation of the 9 fermion piece of the Susie variation has to vanish on its own. And this can be manipulated to a Laplace type equation, where the Laplacian is acting over the moduli space. And there's a tension between the solutions of this Laplace equation and the conformal invariance, which we mentioned earlier. So each of those n scalar structures for the 8 fermion term has a different, it comes with a different solution, or that is, some of them are not harmonic, and only the 4 scalar structure ends up being harmonic. And so there's really only one solution to this Laplace equation, and it tells us exactly what the 8 fermion terms have to be. Okay, and this isn't just some coincidence which happened in 6 dimensions. This 4 scalar structure for the 8 fermion terms is actually very robust, and it's the solution, in fact, for the 8 fermion terms in all of the maximally supersymmetric theories. And it's been seen in many different ways. So I just got a laundry list here of a bunch of maximally supersymmetric theories: quantum mechanics, the 3D ABJM model, n equals 4, 5D maximal, of course, also the 2-0 theory. And it's been seen from supersymmetry methods, just like the ones I just described. In some cases, it can be derived from a one-loop calculation. And in other cases, it can come about from doing a semi-classical instanton calculation. And the fact that it is so robust and it exists in all of these dimensions is really just speaking to how much power maximal supersymmetry gives us over the 4 derivative action, and how all of these theories are related by torus compactification. In other words, it's an example of, I think, at this order, some simple T-duality rules combined with maximal supersymmetry. Okay. Now, continuing though, we'd like to see what constraints we can pull out of the 6th derivative action. In this case, like I mentioned, the top form is not in fact the 12 fermion term, but it's a term with 10 fermions, 1 H field, and then some scalars. But that's okay, we can just continue and take a Susie variation of this term. But in fact, we don't find any longer a Laplace type equation. We instead find a Laplace equation with a source term, so a Poisson equation. But interestingly, the homogeneous equation associated with this Poisson equation has no conformally invariant solution. So again, we're seeing this tension between conformal invariance and the supersymmetry constraints. Now, so that means, though, that because there is no homogeneous solution to this Poisson equation, that the, quote, top form of the sixth derivative action has to be completely sourced by these terms. And these terms are, they come from the two derivative Susie variations acting on the four derivative action, and therefore they're proportional to this coefficient squared. Now this, recall this coefficient was the one sitting in front of the four derivative action. Remember, each of these, delta 2 and L4, were proportional to this coefficient. Okay, so we can already sort of maybe see the end dependence coming out here, where this C4 is going to have some independence itself, and then 6 dimensions, we get some squaring of that. But let's not jump ahead. I just want to take a moment to summarize so far what's been said, because it is important and will show up continuously later. So, so what has been said so far is that we've taken the rank 1, 2, 0 theory of the Coulomb branch and expanded its effective action in derivatives. And we've said that if the four derivative action is proportional to this coefficient C4, 6, then the sixth derivative action has to be proportional to that coefficient squared. That's what supersymmetry tells us. In particular, the West amino terms in 6 dimensions are sitting inside of S6, and therefore they have to have a prefactor proportional to this C4, 6 squared. Okay, but what is C4, 6? So for this, since we don't know the microscopic degrees of freedom of the 2-0 theory, we have to use its relation to the n equals 4 theory. So in this case, we take the 2-0 theory, we put it on a 2 torus, and the KK0 modes then comprise an n equals 4 multiplet, and we have written out the bosonic degrees of freedom here, where the gauge field comes from one of the components of the B field. We still have the same 5 scalars, but now there's a 6th scalar, which is coming out to being proportional to the integral of the B field over the 2 torus. It's a Wilson surface variable, analogous to the Wilson line variables which show up when you compactify regular gauge theory. Gauge transformations of the B field tell us that this 6th scalar is compact, and it has a periodicity proportional to 1 over the volume of the 2 torus. And then combining that, we see that all of the possible values of these scalar fields tell us the moduli space of this theory is locally R5 cross S1. From a string theory perspective, we can see this more easily by saying that originally we had M5 branes in flat 6 space, but now we put a 2 torus along the world volume of the M5 branes. We take one T duality along one of the legs of that 2 torus, and we end up with type 2B with D3 branes with a circle factor transverse to the D3 branes. And this is the moduli space of D3 branes with a transverse circle factor. So everything is nice there. But even though there's the circle factor in the moduli space, we can still go through and play with supersymmetry. And for the 8 fermion terms, we still get this same harmonic constraint. And we can still solve it, where now this time the Laplacian is acting over the whole moduli space, including the circle factor. If we Fourier expand this function in terms of its Fourier modes, because phi 6 is periodic, we find solutions which are Bessel functions. And the argument of the Bessel function is here n, the Fourier mode. R here is the spin 5 invariant combination of the scale of the scalar fields from the 2-0 theory, and Vt here is the torus volume. And since these solutions depend explicitly on the torus volume, we can actually take interpolating limits, where we take the torus volume to 0 and infinity, and we actually interpolate between the solutions in d equals 4 and d equals 6. Finding in the end that whatever coefficient, C44, which was sitting in front of the 4-derivative, 4-dimensional action, so that the action for the n equals 4 degree 9 mils, is proportional to the coefficient sitting in front of the 4-derivative action in 6 dimensions. So even though we don't know anything about the microscopic degrees of freedom of the 6-dimensional theory, we've been able to relate this Wilson coefficient sitting in front of the 4-derivative action to the coefficient in the n equals 4 to action in 4 dimensions, which we know how to calculate because we know the microscopic degrees of freedom in that case. So I want to take a moment just to discuss an interesting aside here before continuing on to the cubic, because I think actually what's come out of this is perhaps the most interesting thing in this research. Forget the cubic, it's cool, but this actually has really interesting ways. This has interesting further directions that we can look at. And I want to just describe this a little bit by an analogy. So the question is, can we interpret this sum of Bessel functions, right? I said the 8 fermion term depends on these Bessel functions, and we're summing over them because it's a Fourier expansion, as counting something, in particular counting instantons. So what does that mean in the 6D theory? Well, let's take a moment and instead look at an analogy where instead we start in D equals 4 superangulars theory, compactified on a circle. And so we have the same setup, though. We have D equals 4 superangulars on the Coulomb branch, right? So we have D3 branes separated from each other, where now this time we have a circle along the world volume of the D3 branes. W bosons from the 4D theory, their world volume can wrap this circle factor, and they get interpreted as half BPS monopole instantons of the 3D theory. And it doesn't just have to be W bosons, it could be full dions. And so they're interpreted as half BPS monopole instantons in the 3-dimensional n equals 8 theory. Now these instantons renormalize 4 derivative couplings in the effective action because they're half BPS. And they come in with some factor that's proportional to the exponential of minus the instanton action, which I've written here as being n the number of times that the W boson wraps the circle factor, multiplied by R here, which is the distance between the two D3 branes, or you can think of it as the tension of a string stretched between the two D3 branes. And then this capital R is the size of the S1, which when divided by the G Yang-Mills squared gives 1 over G Yang-Mills squared in 3 dimensions. So these really are instantons, 3-dimensional instantons. Now you can see this sort of thing coming about from the Bessel sum, which I just described, which has an analog in this case. But you can also see it coming about from a single instanton calculation. If you could do an n instanton calculation, then you could also see it there probably. And this was done explicitly by Dory and Vernachev, and they found agreement between these. Not just agreement with this functional factor, but agreement with the coefficients. And it's been conjectured then that these coefficients really are yielding bulk contributions to some L2 index, which counts the number of BPS states. And they were able to see that in this case, and it was seen also in a similar case of 3D super Yang-Mills flowing down to the ABJM theory by Levon and Safian-Stern. So then we can ask, can you say a similar thing in the 2-0 theory? And I don't think it's crazy to conjecture that this is actually happening. And in particular, so I told you that this was the argument of the Bessel function. So in the limit of large R, the Bessel function has this exponentially suppressed piece. And in fact, it looks like the action of a self-dual string with tension R, which wraps the 2 torus n times. So it actually looks like it's coming from some state in the 2-0 theory, which is a self-dual string, which has a tension due to the n5 branes being separated, and it's wrapping the torus. And this interpretation is corroborated by the fact that had we just compactified the 2-0 theory down to 5 dimensions, we would have no circle factor in moduli space, and there would be no Bessel solutions, Bessel functions showing up in the 8 fermion term. And then from the string theory picture, we would say that the self-dual strings have no 2 torus to wrap. There are no, quote, world sheet instantons for these self-dual strings. In fact, they just wrap the circle factor and become not instantons, but just the instanton solitons of the 5D Yang-Mills theory. So then, we can ask, is there a way to interpret the coefficients in front of each of these n instanton pieces as counting some BPS states in the 2-0 theory? And I think that would be really interesting. Okay. So So let's continue on with the n cubed though, and we're almost there. Right, so we've said that the sixth derivative action is sourced by the fourth derivative action, but everything we've said so far is regarding rank 1 theories, and ultimately we need to get an n in the game because we're looking for an n dependence. So we want to extend to higher rank. Now in the case of the four derivative action in both 4 and 6 dimensions, it can be shown, and we did, that all of the statements I've made extend to any rank, an or dn. Lie algebra, the E case is a little more complicated, but we didn't show it explicitly, but I think that it also will extend there. But there's really no n dependence in that case anyway, so it's not of too much interest to us here. So in particular, what I mean by all statements is the fact that the four derivative action in four-dimensional theories depends on just a single coefficient, which you can calculate from, say, a one-loop computation. And that coefficient is proportional then to the four derivative action in 6 dimensions, regardless of the rank of the A or D algebra.
How does n enter at all? Previous formula you gave us.
Right, so in principle, let me go back. So anytime you see any field here, you just give the field some subscript referring to which brane it's associated with, right? These fields were all just associated with the relative degrees of freedom of 2 branes. But now we just look at the Susie variations which come about, where now we have just n copies of all of these degrees of freedom. So it's in principle much more complicated. You can think there might be a lot of different coefficients which show up, but in fact the entire action at this order is dependent on just one overall coefficient, and then the way that the relative degrees of freedom between the n different copies contribute is just determined by supersymmetry. In particular, they come in as differences. You just look at like a phi A minus phi B as being the relative.
The schematic form you gave us earlier was for a given n5 brane.
Yes. Yeah.
Do I simply take some of those for any, or are there interactions?
Well,
between
there are interactions, and they come about as being sums over differences of these, right? So so each of these fields was looking at. Let me say it this way. So each of this is say a field associated with with the relative degrees of freedom between 2 branes, and now we have n such combinations where we have the relative degrees of freedom between, we have something like n squared of these combinations, the relative degrees of freedom between all of the differences of the branes. And then we just look at the differences that we'll take say a phi sub A minus phi sub B, and degrees of freedom associated with the A brane minus the B brane, and sum over all of these.
So you're
Can you write a typical term like
Yeah,
that?
right now. So what I mean is with d phi A minus d phi B, say to the 4th over phi A minus phi B, I think it came in cubed, and we sum over all pairs of branes. Whereas previously I just wrote d phi to the 4th over phi cubed.
There will be such terms too, still. But in addition, you're saying there will be this one.
We had such terms come out by just saying ignore all of these pieces and just take the product over the phi a's, right? Okay. So I don't want to go over. Does this usually last an hour, or am I already over? Was it
No,
supposed to be 45?
so far so good. And we started a few minutes after the hour on that
So
clock.
I'll take some liberties with that, and I'll be slow. I'll keep you here for a half an hour punishment sort of thing. Yeah. This will be done quickly. Right. So where was I? Was here. Right. So everything we said about the 4 derivative action in 6 and 4 dimensions extends to any rank. In particular, there's just this one coefficient in front of each of the actions, and you can track that. But What I've just said, however, is not true in the case of the sixth derivative action. So that is to say that the sixth derivative action at any arbitrary rank n is not any longer sourced entirely by the fourth derivative action. We can't make that argument anymore. So in order to really find the conformal anomaly, we have to make this whole thing look like an approximately rank 1 problem. So we look at a particular corner of the moduli space where we imagine pulling a single brane very far away from all of the others. And we'll start in the n equals 4 theory in 4 dimensions. We still have all of the branes separate, right? So we're still broken to the maximal torus. But we have an approximate restored symmetry where I've said we started at gauge group G, which is broken to a group H cross U1, where that U1 factor is describing the degrees of freedom living on the single brane, which is being pulled very far away from the others. And H is the approximate symmetry, which is still broken, but in terms, it's broken by terms that are small when expanded in terms of the difference between these branes. Now, the U1 factor associated with that special brane pulled very far away is approximately the dilaton. And we can see that because what I've written here, the definition of the dilaton gives a contribution from each of the branes. This subscript is the same subscript, but just lowercase of what I've written over here, describing which of the branes we're referring to. And in the case where one particular bev gets much larger than the others, then the dilaton gets disproportionately, or maybe you should say it gets proportionally contributions. It gets a contribution proportional to the bev, or 1 over the bev. So really just the degrees of freedom living on this one brane contribute more to the dilaton, and it becomes approximately just those degrees of freedom. Now in this corner of the moduli space, we can decompose the effective action into terms which only depend then on the U1 or the dilaton factors, terms which are approximately H invariant, and then there's some mixed terms. The mixed terms don't contribute to the conformal anomaly, and we can show that just by a scaling factor. In the limit where this brane goes very far away, the mixed terms vanish, and so they can't contribute to the conformal anomaly because that's something which is supposed to be independent on the moduli space. So in particular, though, the Wess-Zumino terms, which are derivatives of the dilaton, show up in this S tau action, and they show up with proportionality, or with a coefficient which is proportional to the difference in conformal anomalies between the ultraviolet, or the G symmetric theory, and the infrared, which is the H cross E1 theory. Okay, so now I told you that the 4 derivative action lifts regardless of the rank to the 6 dimensions. So I've written here the S tau in 6 dimensions, where the coefficient is the same coefficient in 4 dimensions, but the derivative terms are a little different. We pick up some Vev dependence because this d tau to the 4th term is not of mass dimension 6. So there is some Vev dependence which comes about. And similarly, we can decompose the 6 derivative terms into the tau and the H in the mixed pieces, where now the S tau, 6th derivative term, possesses the 6-dimensional Wess-Zumino coupling, this d tau to the 6th piece, plus some others. And so it has a coefficient just by conformal anomaly matching, which is proportional to the difference in 6-dimensional conformal anomalies. S tau is itself just a U1 action, right? It's just dependent, it's just like the rank 1 action, which I was describing before. So we can say the same thing about it being sourced by S4, because it is just the rank 1 action. So in this corner of the moduli space, though we can't say much about how SH and S mixed are dependent on S4, S tau is just the rank 1 action that I was talking about a few minutes ago. And so its top form is again sourced by the 4 derivative action. But in principle, it could be sourced by different parts of the 4 derivative action, the tau piece, the mixed piece, etc. And it turns out, though, that only the tau-dependent supersymmetry variations acting on the tau-dependent 4 derivative action can source the 6 derivative tau action. And we can see that just by saying that the only way to get only tau dependence in the Susie variation is to just use the tau-dependent Susie variations on the tau-dependent action. And so in the end, what we get is that the difference of the difference in 6-dimensional conformal anomalies is proportional to the difference in 4-dimensional conformal anomalies squared. Here's just a bit of a diagram to describe everything I told you. I don't want you going away saying that this is complicated, so I want to push it on you in all different ways. Right, so we start down here in the lower left, in the 4-derivative action in 4 dimensions, where the 4-derivative action is proportional to the difference in conformal anomalies, just by conformal anomaly matching. And this should be S4 comma tau, just the tau-dependent 4-derivative action. Supersymmetry allows us to lift this up to the 4-derivative action in 6 dimensions, where again, the tau-dependent part of the action is proportional to the difference in 4-dimensional conformal anomalies. And again, supersymmetry allows us to use the 4-derivative tau-dependent action in 6 dimensions as being a quadratic source for the 6-derivative tau-dependent action in 6 dimensions. And so we get that the anomaly of the 6-dimensional theory, the difference in anomalies in this corner of the moduli space is proportional to the square of the 4-dimensional difference in anomalies. So just as an example, since I promised an n cubed, we want to get an n cubed, we take, for example, G being SUN plus 1, H as SUN. Then in 4 dimensions, the conformal anomaly is proportional to the dimension of the gauge group. So in both of these cases, so then the difference in conformal anomalies ends up being proportional to n. So we just get an n squared coming as the difference in 6-dimensional conformal anomalies from squaring that. And so we get that the 6-dimensional conformal anomaly is proportional to n cubed in order to get the n squared coming from the difference. So at this point, you may be wondering what happened to subleading corrections and explicit factors. There wasn't an equal sign to be found for a long time. There was, proportionalities. Finding explicit factors is difficult, and the reason goes back to what you were asking, Andy. Really relating these top forms to the West-Semino terms requires a whole orbit of supersymmetry, which is difficult to do, and a lot of coefficients, n independent coefficients, can show up there. Also, subleading and n coefficients can show up in that orbit as well. So finding subleading corrections is also difficult for the same reason. It would be very interesting to do that, to go through and find exactly what explicit factors come out and what are the subleading corrections in n. And if we did, we could do some check, for example, ABS-CFT, to see are the explicit factors agreeing and are the subleading corrections agreeing. So that's a future correction. Right, so the second point is just what I said, finding the, generalizing that. If we found a convenient method, an efficient method to find all of these supersymmetric orbits and the higher derivative actions, relating things, you could use that in a lot of cases. I mean, I know that finding complete supersymmetrically complete higher derivative actions in field theories and gravities would be very useful for lots of people. So finding an efficient way to do that would be interesting. Additionally, there's this issue of can we count half BPS or even quarter BPS states of the 2-0 theory. Where the quarter BPS case here would come about from the 6th derivative action. Right, morally a quarter BPS state in the 2-0 theory will have 12 fermion zero modes, so it would contribute at a 6th derivative order if it were normalizing, say the action on the T2, and then it would contribute in the 6th derivative action. So if we can say something about the half BPS states, we might be able to say something about the quarter BPS states, and that's actually the quarter BPS states would be really interesting because there's been a lot of computations lately about the n cubed specifically coming out of a count of quarter BPS states, describing the, say, junctions of M2 branes when we have M5 branes separated in a non-collinear way. Another thing which I didn't mention in the talk at all is, can we use these symmetry methods on curved backgrounds? So we've seen a lot of use lately of doing supersymmetry on curved manifolds, spheres, and spheres cross circles and whatnot. And for manifolds that conserve all of the maximal supersymmetry, it might be possible to use supersymmetric methods like the ones I've described on those curved manifolds. It's a little complicated though, because once you put the theory on the sphere, there isn't really a conformal branch, a Coulomb branch any longer, because you've given some masses to fields. But I think that's an open question, and I wonder what can we get? Like, can we rederive some of these results from localization and sphere partition functions by using our supersymmetric methods on the Coulomb branch? Or in other words, what does the Coulomb branch action tell us about sphere partition functions? And I've left an ellipsis there for you to come talk to me while I'm here and tell me any future further directions that you might think are interesting, or ask questions. Like I said, I'll be around. Well, thank you.
Thanks a lot. So we have time for some quick questions. All right, now let's thank Travis again, and remember, he's around.